Let's look at another situation that involves business. So some business decisions are interpreted in terms of money, specifically a gain or a loss. So depending on how much money we could make, how much money we could lose, and how likely any particular situation is, can inform a business decision. So let's look at this example. So you're a realtor considering listing a $500,000 house. So you anticipate advertising and open house costs of $5,000. The house is unusual and you're given a 4-month listing. But if the house is unsold after 4 months, you lose the listing and you receive nothing. So you estimate the probability that you'll sell the listing to be 0.3, and if you sell it, you'll make a $30,000 commission. You estimate the probability that another realtor sells the listing to be 0.2, and if this happens, you'll make a $15,000 commission, so half of that amount. Finally, you estimate the probability that the house goes unsold to be 0.5. You will not take the listing unless you anticipate earning at least $6,000 should you take the listing. So if we were to look at just this one situation, there's only 3 outcomes. You either make $25,000, you make $10,000, or you lose $5,000. So specifically, you want to make at least $6,000. Well, if you look at what's going on here, 50% chance that you'll make some money and 50% chance that you'll lose some money. So if you just look at this one situation, there's no way to tell whether or not you would actually make $6,000 from this particular situation. So this is where expected value comes into play. So if we're looking at the expected value for this situation, imagine 1 million houses that looked like this and 1 million different situations where you had this particular combination of gains and losses. If you were to look at all of those situations and log what happened every single time, we're looking for the long run average of what the different outcomes would be. So we're going to go outcome by outcome. We have 3 different possibilities and we want to analyze what would happen in each situation. So possibility 1 is that you sell the house. So what happens if you sell the house? You estimate the probability that this will happen to be 0.3. Okay, but what's the actual numerical value? So if this happens, you'll make a $30,000 commission. Now, do you actually come away with $30,000? The answer is no, because remember, there's a little bit more to it. It says you anticipate advertising and open house costs of $5,000. You have to eat $5,000 regardless. This is your own money that you have to put up front in order to sell the house. So you have to pay money in order to make money, essentially. This $5,000 is paid before we even determine what outcome you would run into. But in order to have even a possibility of selling the house, you have to put the $5,000 up to encourage buyers to come and look at the house. So even though you sell it and make a $30,000 commission, your gain is offset by that $5,000. So your actual gain is going to be $30,000 minus $5,000, which is $25,000. So that's going to be one possibility. If you sell the house after you listed it, then you'll make $25,000, and that's 30% likely. Now, another possibility is the house sells, but another realtor sells it. So you list it, but another realtor actually sells it. And you estimate that probability to be 0.2. Now, if this is the case, you'll make a $15,000 commission. But again, you're paying that $5,000 up front. So ultimately, you come away with a gain of $10,000. So $15,000 minus $5,000 is going to be $10,000. So that's another possibility. In either of these situations, you're making money. So that's good. Now, the third possibility is that you list the house, it goes 4 months unsold, and then you lose the listing. So what happens in that situation? Does it come out to a wash? Well, number 1, we know that the probability of that is 0.5. That's your estimate. Do you break even though? Do you just have nothing and you move on? Well, unfortunately, it's not that simple. Because remember, regardless of the outcome, you still had to put in the $5,000 at the very beginning. So if the house goes unsold, you actually lose money because you're losing that $5,000. It's actually worth negative $5,000 because you have to put that money in up front. You just don't have any additional money to recoup your losses at the very end. So we want to know what's the expected value in this situation. In other words, on average, what do we expect to come out with based on each of these numerical outcomes and how likely each one of them is. So we're going to take each outcome, multiply it by its probability, and then we're going to add up all of those numerical values. So if we do that, the total value is going to add up to $7,000. So make sure, pause the video, take a minute, make sure you can multiply all of these out. You're going to do each product individually, keeping in mind that the last product is multiplied by a negative because you're losing money. And then you add up those subtotals, and that's going to add up to a total of $7,000. So the question is, should you take the listing based on wanting to make at least $6,000? And because the long run average for this situation is $7,000, then the answer is yes, you should take the listing. Now, as with the previous situations, does $7,000 actually represent an amount you could earn, or $6,000 for that matter? And again, the answer is no. You either make $25,000, you make $10,000, or you lose $5,000. So these particular values don't represent actual outcomes for the situation. They're just the long run average. So if you average out all the times you make money, offset by all the times that you lose money, then in the long run, it's going to average out to you making about $7,000 per listing. So in that case, because that meets your requirements, you should take the listing. Now here's another example that is applicable to students. I thought this one was really interesting. So the SAT is a multiple choice test, and each question has 5 answer choices. The test taker must select one answer choice or leave the question blank. A correct response receives 1 point, and an incorrect answer choice receives a 1/4 point deduction. No points are added or subtracted for questions left blank. So in other words, you start with a score of 0, and you're earning points if you get a problem right. You're losing points if you get a problem wrong. If you leave it blank, it just doesn't add anything towards your total. You want to find the expected point value of a random guess. In other words, is there anything to gain or lose on average by guessing? So based on how much you gain versus how much you lose in different situations, is it worth it to guess? Well, think of the 2 outcomes here. So what's the experiment? The experiment is question to question. You're just guessing the answer on the multiple choice question, which has 5 answer choices. So there's 2 possible outcomes per question. The possible outcome that could first happen is you guess and you guess correctly. The other possibility is that you guess, but you guess incorrectly. So if you guess correctly, you gain a point, but if you guess incorrectly, you lose a 1/4 of the point, so negative 1/4 point. Now, what's the probability of each outcome? Again, keeping in mind that you're entirely guessing. The answer choices are random, so each of the 5 multiple choice answers is just as likely as any other. Now, how many ways are there to get the question right? Well, there's only 1 right answer, so there's 1 right answer out of the 5 total choices. So guessing correctly, if you just guess, you're going to guess correctly 1/5 of the time. For that 1 correct answer, though, there's 4 incorrect answers. So the probability that you guess incorrectly is going to be 4/5. So these are the stats for 1 question. And the question at that point is it worth it to guess? In other words, for this 1 question, if we were to look at 1 question at a time, over and over and over again, and average out what happens, all the times you guessed correctly, all the times you guessed incorrectly, what's the average in total that you lose or that you gain from guessing? So you either case to case win a point or lose a 1/4 of a point, but on average, if you repeated this over and over and over again, what does the average come out to? So we're going to take the value that you either earn or lose and multiply it by the probability that that's your outcome. So 1 times 1/5 and then negative 1/4 times 4/5. Multiply each of those pairs together. Again, you might want to pause the video, make sure you can do that, and then you're going to add these together. Now notice it turns into a subtraction because the second product is negative. When you take the sign of that second product, it's going to be negative. So the first product is going to be 1/5, and it turns out the second product is 1/5, but it's negative. So this would be what you earn on average. This is what you lose on average. as it turns out, they're actually the same. So the expected value comes out to 0. In other words, on average, you have nothing to either gain or lose by guessing. Individual problem, you will either earn 1 point or you will lose 1/4 of a point. But on average, just based on what would happen if you had a test with 1,000,000 questions, on average, you're not going to gain anything or lose anything in the long run by guessing. So more than likely the test is specifically structured with that kind of thing in mind, so that specifically you don't stand to gain anything in the long run by guessing. But again, this is a long run kind of thing. In the long run, you won't earn or lose anything just based on guessing on a multiple choice question. Okay, let's look at one last situation. So games of chance, think gambling situations. You have a game of chance and you stand to either make money or potentially lose money. How do you know whether a game is worth playing? How do you know if it's a game that's going to benefit you in the long run where you make a lot of money, or are you going to lose money in the long run? That's the question ultimately. So when we're talking about a game, expected value can be interpreted as the average payoff. In other words, if you played the game over and over and over again, sometimes you win, sometimes you lose, but on average, what do you expect to win or lose if you just played over and over and over again? So balancing out all your wins, all your losses based on how likely each one is, based on how the game is structured, do you expect to win in the long run? Or do you expect to lose in the long run? So games that have a positive average payoff, in other words, a positive expected value, are said to favor the player. So in the long run, those are ones that you expect to make money from. In the long run, they favor the player. Now, games that have a negative average payoff favor the house or the dealer. If you want to think of it as a card game, we can call them the dealer. So those are going to be games where in general you expect to lose in the long run. They're structured so that the player won't benefit in the long run, but the house will. Most games you'll find are intended to favor the house. They're structured so that people can keep playing, and you may win from game to game, but in the long run, if you were to play, say, 1,000,000 times, you will not win in the long run. Now, it's also possible that maybe the average payoff comes out to 0. It is possible that you structure a game so that that's the case. If there's no net average payoff in the long run, then the game is said to be a fair game. In other words, the cost that it takes to play the game, or the amount that you expect to lose in the long run, is the same as the average payoff. So maybe it's a game where you have to pay to play, and then you potentially make some money, or maybe it's just a game where you lose money or make money. But on average, if it's a fair game, then the costs and the payoff actually balance out. So let's look at a couple examples of these kind of situations. So a game is played using 1 die. So if the die is rolled and it shows a 1, 2, or 3, the player wins nothing. If the die shows a 4 or 5, the player wins $3. If the die shows a 6, the player wins $9. If there's a charge of $1 to play the game, what is the game's expected value? And describe what this means in practical terms. Okay, now we're going to assume you start by paying, so you're going to pay your $1 to play, and you never get that $1 back. So you may make some money, they may pay you if you win, but you don't get that $1 back regardless. So what are the different possibilities? Well, technically speaking, there's 6. You could roll anything from a 1 to a 6. But we can condense it down a little further by thinking about the different winnings and losses depending on the different rolls you make. So if you roll a 1, 2, or 3, you win nothing. So that's one combination where you win nothing. But again, it doesn't come out to a wash because you had to pay that $1. So you actually lose $1 if you roll a 1, 2, or 3. So the house gets to keep the $1. Well, what's the probability that you lose $1? Well, out of these 6 different outcomes for the particular game, 3 represent ones that would lose you $1. So the probability that you lose $1 is going to be 3 out of 6. Now, if you roll a 4 or a 5, you win $3. But again, you had to pay your $1 up front, so you really only come away with a gain of $2. Now, how likely is it that you come away with $2? Well, there's 2 ways that you come away with $2 out of the 6 total possibilities. So the probability that you make $2 is going to be 2 out of 6. And then the last possibility is that you roll a 6. If you roll a 6, you win $9. But again, you paid your dollar up front, so in total you come away with $8. There's only one way to make $8, so 1 out of the 6 total possibilities represents you making $8. So we multiply each value by its probability, add up the totals, so make sure you can do that. And that's going to come out to a numerator of 9, so -3 plus 4 plus 8 is going to come out to a numerator of 9, and then it's divided by 6. So 9 divided by 6, and we're talking about a dollar amount. Now, how do we know it's a dollar amount? Well, each of the products has a dollar amount, and then it's multiplied by a fraction that doesn't have a unit. So dollars plus dollars plus dollars gives us dollars at the end. So we know the expected value is a dollar amount. It's 9 divided by 6, and if we actually do that division, that comes out to $1.50. So the expected value of this game is $1.50. In other words, if you play this game over and over and over and over again, sometimes you lose $1, sometimes you win $2, sometimes you come away with $8. But in the long run, if you average out all your winnings, you average out to winning $1.50 per game. Now, because this is a positive average payout, when you play the game, that means this is a game that favors the player. It means in general, this would be a good game to pick to play, because in the long run, you do expect to make money on average in the long run. So again, sometimes you lose, sometimes you win, but in the long run, it averages out to you winning about $1.50 per game. Okay, let's look at another couple examples. A charity holding a raffle sells 1,000 raffle tickets for $2 each. One of the tickets will be selected to win a grand prize of $1,000. 2 other tickets will be selected to win consolation prizes of $50 each. Find the expected value if you buy 1 raffle ticket. Okay, so what are the different possibilities in terms of your gain or your loss here? Well, you either win the grand prize, only one person's going to win. You could win a consolation prize. There's 2 ways to win the consolation prize. Or you win nothing, and most people are going to win nothing. So if you win the grand prize, what do you win? You win $1,000, but remember you bought 1 ticket for $2, so you really come away with $998. Now, out of the 1,000 tickets, you only bought 1. So if there's a bowl full of tickets and they're drawing tickets out of the bowl, only one of those draws out of the 1,000 represents you actually winning. So 1 out of 1,000 is the probability that you'll win the $998. Now, what about the consolation prize? 2 tickets are selected to win $50. So $50 minus the $2 that you paid comes out to a gain of $48. Now, you have 2 chances to win this particular amount because there are 2 draws made. So draw 1 you could win, draw 2 you could win as well. So 2 chances out of 1,000 to actually win the consolation prize. Now, any other combination, you win nothing. So you paid your $2 and you don't get anything. So you lose that $2. And all the 997 other tickets in the bowl represent people who are going to just lose their $2 and come away with nothing. So the probability of winning nothing is going to be 997 out of 1,000. So we multiply each value by its probability. Make sure you can do that in the calculator. We add up those amounts. So these are also going to be dollar amounts. Our fractions are unitless, but the numbers the fractions are multiplied by are all dollar amounts. So dollar amounts added up together yields a dollar amount. When we add up all these individual values, it's going to add up to negative 90 cents. In other words, on average, you're going to lose. That's not surprising. There's a pretty big win, but it's extremely unlikely, whereas losing money is very likely. So the likelihood of you losing very much offsets how much you could win if you win in that one time out of 1,000. So this would be a scenario that favors the house. In the long run, you don't expect to make money. Case to case, you're either going to win $9.98, you're going to win $48, or you're going to lose $2. But if you were to look at this situation a million times, on average, you come away with negative 90 cents if you average out all your wins and all your losses over all the times you played this game. And then let's look at one final example. So one way to bet in roulette is to place $1 on a single number. So we have 1 out of 38 numbers. We have 1 to 36, and we have a 0, and we have a double 0. If the ball lands on that number, you are awarded $35, and you get to keep the dollar that you paid to play the game. If the ball lands on any one of the other 37 slots, you're awarded nothing, and your dollar bet is collected. So find the expected value for playing roulette if you bet $1 on number 20. Okay, so what are you doing? You're betting your dollar, so potentially you're going to lose your dollar, okay? And then you're betting on a specific number. You're betting on number 20. Well, what are the two outcomes? Either they spin the wheel and it lands on a 20, or they spin the wheel and it doesn't land on the 20. Each of those represents a different gain or loss for you. So what if it does land on the number you bet on? What if it does land on number 20? Well, you're awarded $35 and you get to keep your dollar. Now, does that mean you make 36? No, it doesn't mean that. You're putting your dollar down to play, so you're giving them $1, you're losing that dollar. And then if it lands on your number, they're giving you your dollar back. So you didn't actually make that dollar, you just didn't lose it. So that is balanced out. You pay your dollar, you get your dollar back, it's balanced out. You're making $35. So if the ball lands on your number, you're making $35. And again, that dollar that you paid, you just get that back. So that doesn't represent a gain or a loss, it's just breaking even at that point. Well, what's the likelihood that that actually happens? Well, you bet on a single number out of the 38 in total. They're all equally likely because the wheel is balanced and all the spaces are sized the same way. So out of the 38 total, you bet on a single number. So the probability that it lands on your number is going to be 1 out of 38. So winning $35, it's a probability of 1 out of 38. Now, the other possibility is that it does not land on your number. So if it lands on any number besides 20, what's the situation? Well, you bet your dollar, you paid $1 to play, but you don't get anything. So your dollar bet is collected. They keep your dollar and you don't get anything. So if it doesn't land on your number, you lose that dollar. So you're down $1. Well, what's the probability that you're down $1? Well, how many ways can you lose? Well, there's only one way to win. All the other numbers on the wheel, in other words, the remaining 37 out of the 38, represent you losing. So the probability that you lose is going to be 37 out of 38 because there's 37 numbers that represent a loss out of the 38 numbers on the wheel. So one number represents you winning out of 38, and 37 numbers represent you losing out of 38. So we take each value, multiply it by its probability. So our first term is going to be positive. That's the amount on average that we could win. And then the second term is going to be negative. That's the value on average that we lose. So 92 cents minus 97 cents comes out to negative 5 cents. So on average, in the long run, if you play this game over and over and over and over again, you expect on average to lose 5 cents per game in the long run. So there's a bunch of different ways we can apply this concept of expected value. I want you to notice that the procedure for finding the expected value is going to be the same in any situation. We're thinking about numerical outcomes in our situation and then how likely each outcome is versus another outcome. We take the value of the outcome, multiply it by its probability, do that for all the different combinations, and then we take the sum. So that sum just represents a long run average. If we were to look at this situation multiple times, what would we expect to happen in the long run on average? That's going to be our expected value.